gives you R matrices and this kind of fusion structure. So you have A of algebra, and then you have a universal R matrix. So you have an element R in A tensor A. And it obeys this condition, this kind of quasi-triangularity condition, which allows you to construct R matrices for tensor products if you know R matrices for the factors. Ordering of factors. Equal R13, R23, R2, sorry, and delta. So this would be identity times delta. You act on the second factor of A, and if you act on the first factor, you get R13, R23, I guess. So, and again, so there is a picture that somehow you should think of the coproduct as something like this. You start from A, you will do it as A, and it is equal to probably the second one. And so, and this actually implies the Yang-Baxter equation. And and then if you have this structure, then you can go to any representations and construct an R matrix for any pair of representations. And if you obey the Yang-Baxter equation for each triple of vector spaces. Moreover, using this quasi-triangularity structure, you can construct new R matrices for tensor products of the representation for which you know the R matrices. So that's the story. And let me first give the example, and then I will say something about how to correct this in order to have more trivial examples. I think the examples of these are kind of rare. I mean, interesting, but so you need to complete and introduce topology and stuff, which I don't want to do, but I will explain it in the example, and then you see what just to do. So the example is this UQ of SL2, so it is a Q deformation. So Q is exponential H bar, and so for H bar equal to 0 or Q equal to 1, you should reproduce the usual story. So here you have three generators, H, E, and F. This is SL2. In the SL2 generators, you have or maybe U of SL2, you have that Matthias Tog called, I don't know, K plus, K minus, and 2K0, and which obey the standard commutation relation. You want to deform them. So in UQ of SL2, we have generators EF as before, and then Q to the H, which is called K. Some symbol for generator K, and the relations are deformed, so you have K inverse is Q square E, A inverse is Q to the minus 2F, and the commutators, and this would follow from the usual relations if you write K equal to Q to the H, and then the commutator of E and F is Q deformed, so you have K minus K inverse divided by Q minus Q inverse. So in the limit Q goes to 1, or H bar goes to 0, and Q to the H, it will converge to H if H bar goes to 0 or Q goes to 1. Right, and then you have the coproduct. The coproduct is given on generators by these rules. So it's not co-commutative, right? It's not invariant in the permutations of the factors. And you have f times q minus 1 plus 1 times f, and you have formulas for s and for the antipode and so on, but maybe I will not write everything. What I want to write is the formula for the R matrix, and then this explains what Wilson has to say about how to improve this formulation. So the R matrix has the following form. It's exponential of h bar over 2, h tensor h, sum j from 0 to infinity, q to the 1/2 j plus 1, y minus q inverse j, divided by q factorial of f to the j tensor e to the j. So first of all, it's an infinite sum, and so you have to make sense of this. So, and q factorial is q numbers, n is q to the n minus q to the minus n, divided by q minus 1, and n factorial is the product of q numbers from 1 to n. So, first of all, it's an infinite sum, and this is not really a problem because in any finite dimensional representation or highest weight representation, these powers of E or F are 0. Right? So it's well defined in any representation. So, and here, then this, I mean, I wrote Q and I wrote H bar. This is not really in the algebra because you have, if you say that the algebra is generated by K, you don't have H, you don't have the logarithm of K. But again, in any representation, H will be diagonalized, let's say finite dimensional representations, and then this will make sense. So there are these two things, and then there are kind of two versions of the story, or three versions maybe. Versions. So the first version is you do it like this. You take you do it as an algebra over a rational function of Q, and then you don't have an R matrix, still strictly speaking, but still in any finite dimensional representation this makes sense, which is fine. Or you take Q to be a non-zero complex number. This is the first thing, and then if you really want to have an R matrix which is well defined, then you take it as an algebra over H bar. So it's a topological algebra. So you allow, so generated by E, F, and H. So it means that you allow this element here, for instance, which is an infinite series in H bar, but any coefficient of H bar is some well-defined element. And then you have to take, then there exists an R, it's quasi-triangular. With R in some topological completion of this. It's an infinite series, then it's really quasi-triangular in this sense. But if you, right, so, but then if you evaluate this in representations, then it is fine. So I think this formula was first written by Mark Rosso. And so there are such formulas now for any dimensional or affine Kazmudi algebra. Okay, so, so I think I missed the main fact here. Sorry. So this R is supposed to have the main property of R is that R of delta of X interpolates with the coproduct with the opposite coproduct. So delta prime of x, so for all x in the algebra, is sigma composed with delta of x, and sigma is a permutation of the element in the algebra. It's the opposite coproduct. And this is what you need. So I mean, this will say that, so if you have any two representation, V and W representations, and you evaluate your R matrix in these two representations, and then you compose with the permutation of factors in the representation, this will be an isomorphism between the two ordering, isomorphism of representation. So this property implies this one in any pair of representation. So R itself is an isomorphism of V tensor W. So you compose with P, you get an alpha of V tensor W to W tensor. Okay, so that was the main property.
That main fact, R delta is delta R, that's the quasi-triangular?
Sorry?
Is that the quasi-triangular property?
I think quasi-triangular is this maybe that, I don't know if it has a name in itself. Okay, so...
Excuse me, sir. What was P? Wasn't it just sigma?
P, yeah, but sigma is I prefer to distinguish because P is a permutation in the representations and sigma in the algebra, but it is the same operation, right? Maybe I should write P VW or sigma VW or something like this. Okay, so so you can read about these things. There are textbooks for I think the one with more details is the book of Charlie and Presley. Okay, so let me say something about representation theory of UQ. So I don't want to give the general theory now, but I want to say something more about UQ of SLN and UQ of, maybe UQ of GLN. But so it's given by the same type of formula. And also, so the examples that we want to study are this one and UQ of SLN hat, which is the central extension that Matthias was also talking about. So, so before going to UQ, you have this SLN. So maybe first SLN. So, so to understand this, it's good to have this Chevalier-Serre presentation. In the classical case, so the remark is that if you take SLN, for instance, is generated as a Lie algebra by EI, which are EII plus 1, so this is the matrix with the 1 in the position II plus 1 and 0 elsewhere, and Fi equal to EI plus 1I. So in the SL2 case, they are the ones that we have there. And I think that's enough, but it's useful also to have the HI, their commutator, which is EII minus EI plus 1, I plus 1, which is H in SL2. And so here I goes from 1 to n minus 1. And then you can define this, you can define this, the algebra by giving the commutation relations between these, or some relations between these that will imply all relation of the algebra. And then we write these relations, but before I want to, maybe I will want to write them in the case of SLN hat. So SLN hat is a central extension of the loop algebra, which is LG is equal to C, sorry, G, the inverse. So, right, so so Matthias wrote the relations, so I will not. The central extension, so we see them again. And so it's generated by you have again this EI-FI as before, so because you have the constant loops which are generators of SLN, but then you have E0, which is N times T, and F0, which is E1N times T inverse. So it is easy to convince yourself that you can get any loop, and then there is a central end. But any element of the loop algebra you can hook up by taking iterated commutators of these things here. And so, right, you can increase and decrease the power of T, you can get them all out of them. And then, so it's useful to have relations which involve these generators, and then this was a starting point maybe to define what is a Kac-Moody algebra. And right, so this would be the story. So and then I will write a generalization of that formula there for UQ of SLN hat, and this will also contain as a subalgebra UQ of SLN. And so the relations between the generators are the following. So it's more or less is Aij, I will say what is Aij, Ki, and J, Ki inverse is Q to the minus Aij. And the EI J is delta Ij, Ki, so the generators EI, Fi, Ki, and here I goes from 0 to n minus 1, and then you have the same formula that we have there. And then you have the so-called Serre relations, but maybe I will not write them. So e.g. that EI, EJ is 0 if if J is different than I plus minus 1 mod n. Something like this, and then there is a third order relation, but I will, and also for F. Okay, so these are the relations basically. And so in the limit, when Q goes to 1, these are the usual relations. And this matrix Aij is the Cartan matrix of SLN hat. There's 2 on the diagonal, minus 1. And you have a little minus 1 on the corner. So if you take the submatrix, this is the R matrix of SLN, so the Cartan matrix of an minus 1, and and UQ of Selen is a subalgebra generated by EI, FI, KI with I positive. So this is the picture, and then you have a formula for the coproduct, for the antipode, and so on. So let me just give the coproduct, which is the straightforward generalization of what we have there. And delta Ki is equal to Ki times Ki. Okay, so you can check that this is indeed a product. So the formula for the R matrix is much more complicated, but this you don't really need in the concrete construction, because you can directly construct the R matrices in representation. So let me say something about representations. So there are kind of two kinds of representations of this algebra. So one is the kind of highest weight representations. So here maybe I should say that the remark is that K0 up to Kn is a central element. So this has to do with the central extension. And it has to do with the fact that this matrix is positive semi-definite and it has a kernel. And so this is a central -1. Okay, so you have highest weight representation of the types that maybe so. Yes, was more general there, but so this would be killed by the EI. So it would be generated by a vector which is killed by the EI, and for those, you know, these kind of expressions make sense because you have E's on one side, and then you have, for instance, finite dimensional representations. And they are not highest weight, and so I will give some examples of those. And so the theory here is very different than the theory here.
So if it's finite dimensional, how can it not be highest weight?
Right, not for the Kasmoudi algebra. So let me. Because so E0 is not.
But then this would be sort of the central extension will be
trivial, yes. So here you have some level K, so the value of, and here you have level 0. So it means that this central element is equal to 1. So let me give some examples of this story here. So the main example is a vector representation. So you take V equal to Cn, and if you look at it, it will be a very stupid representation. In the sense that you just take the vector representation of the algebra. So maybe I will say, so with evaluation point, in C star, namely, so it is analog of the representation that of the loop algebra. Q analog representation of the loop algebra, which takes G times, I don't know, some element A times a function f of t, a polynomial, Laurent polynomial f of t. It maps it to A times, so on a vector V. You evaluate it at a point Z, and you act with the vector representation, the usual defining representation for SLN on V. Right, so this would be the vector representation V of Z. And so, let me give you the formula. So the formula will be the one you expect. So EI on EI will be mapped to EI I plus 1, and FI EI plus 1I. So this is what you do in the so this is for UQ of SL hat. This is for I positive. And then KI will be sent to, right, Q to the AI. I plus 1, I plus 1. So you are not really doing it, you are taking the same representation and take Q to the H to define K. And I will explain why that works. And for E0, you will again do this N0, N1 times Z times Z and F0 to E1N Z inverse. So, so the remark which explains why this works, so if you take the generators, I don't know, HI, then this is really sent to HI for the vector representation. The reason is that if you have Q to the H minus Q to the minus H divided by Q to the Q inverse, which is the right-hand side of these commutation relations, somewhere also for SLN here, then this is equal to H if H is diagonalizable with eigenvalues one or minus 1. So it doesn't really matter that you quantize as long as you have this vector representation. So, but it doesn't mean that the theory is the same as the classical case, because by taking tensor product you can generate new representation, for which you have a non-trivial action of this right-hand side. So maybe one remark about this evaluation point story. It comes from the fact that you have, for each complex number z, different from 0, you have a homomorphism from the loop algebra to the original algebra, the algebra, which is evaluating t equal to z. And this does not quite work for general Kac-Moody Lie algebras, but you still have an automorphism of the Lie algebra which kind of shifts this z. And so this is this representation V of z is a twist of some representation V by an automorphism.
So this automorphism is basically the Virasoro algebra that comes from the Shugawara expression, or how should I think of this?
No, it's kind of more trivial. So the automorph, you have an automorphism tau z, which is trivial on the I and Fi for I positive, and tau z of E0 is z E0, tau z of F0 is the inverse F0. it shifts the.
And that's also what the Shugawara L-1 would do, right? Because then you commute with the zero modes and on the...
So, but it has the same for all levels, right?
But I mean, in affine language, the EIs with I greater than 0 are the zero modes, right? So
Sorry, not. So what did you say? So
I mean, the EIs with I bigger than 0, they're the zero mode, they're the finite dimensional EIs. So the Virasoro generator would commute with those, right?
Right.
So that would mean that the conjugation with e to the L-1 or whatever wouldn't do anything on them. And then E0 is the -1 generator of the highest root or minus the highest root or something.
That's right.
But Virasoro is sort of inner, right? And this is not at all, right? Virasoro, you kind of realize by the Shugawara formula, and I think here at level 0 probably.
But the automorphism, yes. Yeah, maybe, but probably you are right. That this is the automorphism is.
But I mean, level 0, Shugawara still works, right? As long as the dual Coxeter number is non-zero.
Yeah, I think you are right, actually. Yeah, you. But yes. Yeah. Right. Yes. Right. So you have this kind of derivation in the full Kac-Moody algebra, and this would be the exponential of the derivation. Right, then I have the formula for the. Okay, so this representation of the V of Z is an example of a so-called type 1 representation, where Ki into the Hi, where Hi is diagonalizable. Integer eigenvalue. And there are also other types, but they are kind of related to it. You can still multiply by -1 or up to signs. This will be classification of these is essentially classification of finite dimensional representations. And then you can construct new by taking tensor products. For instance, you can take V of Z1, V of Z2, and this turns out to be reducible for we will see a little bit of it in the exercises, for generic Z1, Z2, and so if you believe that there exists an R matrix, which is not clear, right? It's not clear that an R matrix exists. So it would be now I will call them R check R matrices because I compose them with the permutation. It's not clear that an R matrix exists. So we know that there is this kind of formal power series which is the universal R matrix, so we should evaluate it in this representation. But this is actually a genuinely infinite series because you don't have this highest weight condition which breaks the sum. So you should ask if it converges or not, and sometimes it converges and sometimes it doesn't. And it converges if these are, we will see that there will be points where it is not defined. And so, but since they are irreducible, then if it exists, it will be unique up to scalar. So then one can write down the condition of this being a homomorphism, and this will determine you the matrix and formula that actually it will depend on the ratio of the spectral parameters. So this will be a multiplicative notation with respect to yesterday. So ratio instead of differences. This is essentially because it will commute with the action of this automorphism, which is also an automorphism of algebra. And so R of Z has this interesting formula. Well, I will say why it is interesting, but now I just write the formula. So this is a formula written by Jimbo, but it is essentially the R matrix for the 6-vertex model of Baxter. So the details are not important, but I would still like to write it because it is an interesting feature. Okay, so this is some formula. And theta of I is 1 if I is positive and 0 if I is less than 0. This is an observation of Jimbo really, that this can be written as
Sorry, you write those factors inside the sum just by convention. You can write the
right, yes.
Okay.
Yes, yes. Sorry, yes. Except here, I mean.
Yeah.
Okay, so I from 1 to n, and so Jimbo wrote it in the following form. So there is some factor. So I want to get rid of those denominators. But if you get rid of the denominators, you have a polynomial of degree 1 in Z. So, and this polynomial has the following form, Z times T minus T inverse. And T is T obeys the Hecke relations. Relation. And so for q equal to 1, this is t squared equal to 1, which means it's an involution, but here it is a relation, and we'll come back to this in a second. And then, right, and so this makes the connection with the Schur-Weyl duality, which maybe I will explain now. To say. So maybe a little more I want to say is that in this general Kac-Moody stories, or even if in this case for the finite dimensional SLN, you have a highest weight theory. So if for finite dimensional SLN, this is the highest weight representation. And for that there is this story of highest weight modules. So just maybe type 1 representations of SLN, of UQ of SLN. So we have a highest weight theory. Namely, all finite dimensional representations, all irreducibles, finite dimension, like in the classical case, representations of UQ of SLN. For Q, Q not a root of unity. Are highest weight.
So this is highest weight in the sense of the Lie algebra rather than in the sense of the Kac-Moody algebra?
Yeah, but here I take the SLN, the finite dimensional SLN. Right, so for Kac-Moody it is more subtle. There is a version of highest weight theory also for Kac-Moody, but it's So it means that it's generated by some highest weight vector V lambda. Lambda is a partition or dominant weight. So it has a property that EI V lambda equal to 0 for I from 1 to n, right? So it's finite dimensional. Then you can take evaluation points, but this is basically the story.
1 to n minus 1 or?
Minus 1, yes.
These lambdas are integers over.
Integers, yes, like partition, so it is integers. And the ki is q lambda I minus lambda I plus 1. So the lambda I are, if you like, the eigenvalues of the GLN generator, so these are differences. And so they are V lambda. And then out of them you can construct representation V lambda Z for Z in C star representations of Q of SLN hat. And then you can either tensor products and basically this is the whole story. All the representations, so for generic Z1 up to Zn, these are irreducible, so generically irreducible. Okay, but in the classical theory, you also know that the representation can be obtained from the vector representations by taking subquotients of tensor product. And this is this Schur-Weyl story. Schur-Weyl. Duality. So this first, let me recall what it says in the case of the classical case of Q equal to 1. So there you consider the vector representation of SLN. So we are not cut smooth here. We are finite dimensional SLN, and then you can construct V tensor V, small n copies. And here you have two actions. You have the action of GLN, of SLN, of the Lie algebra, or the Lie group actually also. And you have the action of the symmetric group, because you can permute the factors. And so to state the theorem, it's better to take algebra, so you take the universal developing algebra. And here the group algebra of Sn, and they are, so these actions are, these algebras are commutants of each others. Is it the correct word, commutants? Namely, you have an action of U of SLN, and you ask what are all the operators on the tensor product which commute with this action for all SLN. And the answer is these are exactly the linear combination of actions of permutations on the factor. And this means that you have the so-called multiplicity-free decomposition of your representation space. Namely, you have that V times n. You want to the power n. You would like to write it as a direct sum over representations of V lambda times W lambda So these are representation of SLN, and these are representation of the symmetric group.
S little n.
Yes.
Little n, yes, thank you. And so they commute. So these are multiplicity spaces for the representation for SLN, and these are multiplicity space for the representation of Sn. And so each lambda appears once, right? So the multiplicity space is irreducible for the action of the other action. So this is a story, and then so if factor n is big enough, then you take all partitions of. So we have certain sum of over partitions. So this is the story for U of SLN, and what Jimbo did, he did generalization to the quantum group case, and he observed that you have to replace the symmetric group, or the algebra of the symmetric group, by a Q deformation, which is a Hecke algebra.
So that's for the affine case, or that's for UQ?
Yeah, in the affine case, if you take the tensor product, it's irreducible for generic Z. And for special Z, it is not like this that you have a direct sum of subrepresentation. You have some kind of non-trivial extensions. And I will give an example because it will be useful. Today. So at what time should I stop?
It's a little bit negotiable, but you know.
7 minutes, 8 minutes.
Okay. Let's agree on 8 minutes.
Swiss precise prediction.
Okay.
Right, so maybe we just basically say. So now, so Jimbo. So you consider now again the tensor product. This is finite dimensional. Later we will see also that's moody, but finite dimensional SLN. So here you have two actions again. You have UQ of SLN, and you have the so-called Hecke algebra. So what is a Hecke algebra? So the Hecke algebra is generated by Ti. So you have small n factors. And minus 1. And you have relations which are the so-called braid relations. If the difference is bigger than 2. And Ti plus 1. So these relations are also satisfied by the symmetric group, the transpositions of the symmetric groups, transposition of R minus 1. But in the symmetric group, you have the additional relation that Ti squared is equal to 1. And so these are the braid relations, so that the relations of the braid group. And then you have this additional relation which I wrote before, plus Q. And so this is the Hecke algebra. You have all the singulars of Hecke algebra. And so how does it act on the tensor product? Yes, so the Ti are this operator T that appears in the matrix, and you act on the ith and I plus first factor. And so this is also called Baxterization in some sense, so maybe the exercise is that. So, and again, so this is the theorem of Jimbo is that these are commutants of each other.
The modules of Hn, the definitions of modules of Hn.
Yes, exactly. So you have a parallel theory, so you again have a decomposition of the same type, same partitions appears, and the representation of the symmetric group deforms into representation.
So what is Z here? Z is still, Z only appears in the F1 case, or did I misunderstand that?
Where is that?
I mean, upstairs on the blackboard you have R of Z, right?
That's right. So the remark is that if you factor out the denominator, you get a linear function of Z. So a fine function, and then I define the coefficient to be TT inverse, so they are independent of Z. There's some kind of combination of this EIJ, and these obeys this. So maybe the exercise that we didn't, maybe for the next session, is to check that they use the Yang-Baxter equation. Factor doesn't play a role in the Yang-Baxter equation for Vt minus T inverse from the Hecke relations. So this Hecke relation.
That be true for any value of Z? Or
Sorry?
for any value of Z?
Yes, so right, so T obeys these braid relations. And then now if you take T and T inverse, so I should say that T should be invertible. If you take this combination out of these relations, you can deduce the Yang-Baxter equation with respect to R.
And the other way around, the Yang-Baxter implies declarations or not really?
Probably if you assume this form, probably it follows, but you cannot really assume that in general. Right. Okay. So what is the other application of this Hecke story? Is to understand this decomposition of tensor product of evaluation representations. So did I still have 3 minutes? So now, out of this representation, I would like to construct the other representations with higher partitions by this thing here. But I would like to do it in the Kac-Moody case, in the affine case. So now let's look at SLN hat. So we know that that we have that V of Z1, V2. So this will be an exercise in the classical case that this is irreducible. It will be today in the exercises. Z1 is not equal to Z2. But if they are the same, then this decomposes as a symmetric copy of the symmetric representation, and you can take symmetric and skew-symmetric tensors, and it's a decomposition into irreducible representations. So now we would like to do the same in the quantum case. And what happens is that something special does not no longer happens when Z1 is equal to Z2, but when Z1 is equal to Q squared Z2, or something like this. And namely, if you look at the R matrix, it is not defined if Z is Q to the minus 2, and you can also check that it is not invertible if Z is equal to Q to the Q to the 2. This can be also seen from here, because for special values of Z, this will be a projection onto the eigenspaces of the two eigenvalues. So the story, so now in UQ of SLN hat, then you have usually that R hat of Z1 over Z2 is usually an isomorphism. For Z1 different from Z2. But if they are, then you have, I think you have R hat, say Q squared, or Q to the minus 2. So this is not defined. You have to take the residue. You have to take out this denominator. We call it reg. Now take the residue at this point. This will be a map from Z, what is it, Z, Q, minus 2, so I want to write it in this way. Right, so the ratio is Q minus 2. Will be a map between these two spaces. And so the kernel is a proper subspace, sub-representation. And this we will see, but now maybe my time is over. So we'll see with the Hecke algebra, and so you can take the kernel, the co-kernel, and this will give you a definition of the quantum symmetric and skew-symmetric algebra. But it turns out that this sub-representation does not have a complement. It is not specific. Okay, so I will come back to this, and then I will explain how to generalize this Weyl duality with this Howe duality, where instead of V, we take copies of fundamental representations of okay, thank you.
Questions or comments?
The operator coming from the matrix.
That's right. So the braiding, right? So in the finite dimensional field, we have a matrix. The braiding matrix, and these are matrices you get by sending this to 0 or to infinity. One are the braiding matrices of the finite dimensional. So this is really the braid representation of the finite dimensional.
There is a question about terminology. So far as it goes, theory of Reshetikhin modules, is it that's it, or is it something else? Right?
Yeah, these are special cases. So I think, so the Reshetikhin modules correspond to rectangular Yang diagram. So these are special cases. So this would be this partition and this partition.
Okay. So if there are no more questions, I thank you all again.